Hello. In the previous lesson, we discussed about the different registers associated with the EEPROM operation. In this lesson, you will learn about different programming operations of the EEPROM memory. Let's start with the erase and write operation. The EEPROM erase and write operation is a time-consuming operation, and specific steps must be carefully followed. The flowchart shows the steps to write the values to the address, data, and control registers. The first step is to check if the EEPE bit in the EECR register is 0. If it is not, the previous write or erase operation is in progress, and we must wait for it to become 0. Once the EEPE bit becomes 0, then the address register pair, that is EEARH and EEARL, must be initialized with the address. This happens in two instructions. I have shown to set the EEARL first, then EEARH, but the order can be changed. Then the register EEDR is initialized with the data to be written in the EEPROM memory. Now the EEMPE bit in the EECR register must be set. Then EEPE bit in the EECR must be set to 1 within the 4 clock cycles. In the usual scenario, these steps for write operation works fine. But when the system complexity increases and number of tasks and interrupts handled by the microcontroller increases, a few precautions must be taken. There is possibility that an interrupt may occur between the step 5 and 6. In such case, the write operation fails since the constraint of setting EEP bit within 4 clock cycles is not respected. Furthermore, if the ISR interrupting the write operation accesses EEPROM for any operation, the EEAR and EEDR register will be modified, causing the interrupted EEPROM access to fail. To mitigate such cases, it is recommended to disable the interrupt by clearing the global interrupt flag before setting the EEMPE and EEPE bits, and enable the interrupt back again after the operation is completed. When the write access time has elapsed, the EEPE bit is cleared by the hardware. The user software can poll this bit and wait for 0 before writing the next byte. When EEPE has been set, the CPU is halted for 2 clock cycles before the next instruction is executed. The logic for write operation seems fine. We have taken care of occurrence of interrupt during the write operation. But what if the development board resets during the operation? In such scenario, microcontroller ensures the write operation is completed before the boot up sequence is initiated. But this is possible only when the power supply voltage level is sufficiently high for successful write operation. Now, let's look into the erase only operation. In this operation, a byte in EEPROM memory is erased and the value FF in hex appears at the erased byte location. Erase operation is very much similar to the write operation. The first step in erase operation is to initialize EEPROM into erase only mode. It is done by assigning the value 0, 1 to the EEPM bits in the control register. The completion of previous write operation is then checked by polling the EEPE bit for 0. If the EEPE bit is cleared, the EEPROM memory is ready for erase operation. Then the address register pair, that is EEARH and EEARL is initialized with the address which needs to be erased. In erase operation, the content of EEDR register is ignored. Since the steps in erase only operation is the same as that of erase and write operation, we follow the steps as in the write operation. The interrupt is disabled and then EEMPE bit in the EECR register is set. Then the EEPE bit in the EECR register is set. The constraint of setting EEPE bit within the 4 clock cycles also applies here. Then the interrupt is enabled back again. This completes the erase only operation. The steps in the write only operation is very much similar to the erase only operation. The first step in write only operation is to initialize the EEPROM into write only mode. It is done by assigning the value 10 to the EEPM bits in the control register. Then the completion of previous write or erase operation is checked by polling the EEPE bit. This bit must be cleared for the operation to proceed ahead, else the operation must wait for the bit to be cleared. Then assign the address to the address register pair. Then the data to be written to the address pointed by the address register pair is written to the EEDR register. As in the erase and write operation or in erase only operation, the interrupt is disabled by clearing the I flag in the status register before setting the EEMPE and EEPE bits. Again, the constraint of setting the EEPE bit within the 4 clock cycles after setting the EEMPE bit holds in this operation too. Then the interrupt is enabled back again. This completes the write only operation. Similar to the previous operations, the EEPROM driver must poll the EEPE bit before starting the read operation. If a write operation or an erase operation is in progress, it is neither possible to read the EEPROM nor to change the EEAR register. Once the EEPE bit is cleared, the address register pair is set with the address of the EEPROM memory byte to be read. Then the EERE bit in the EECR register is set. This causes the EEDR register to be assigned with the content of the EEPROM memory address. Now the driver can pass the data read to the application for its consumption. The EEPROM data may get corrupted during low power supply voltage because CPU and EEPROM may not operate properly. There can be two reasons for the data corruption. Firstly, the EEPROM write sequence requires steady voltage supply during the write operation, which is quite long. Secondly, the CPU can execute the instructions incorrectly in the case of low voltage. The data corruption during low voltage can be avoided by keeping the AVR reset active during low voltage. This is done by enabling the internal brownout detector. If the detection level of the internal BOD does not match the needed detection level, an external low VCC reset protection circuit can be used. This is a measure taken at the hardware level. The driver software may implement checksum calculation if data integrity is critical. The checksum detects any corruption of data in the EEPROM memory. The checksum byte is an extra byte that is associated with a series of data bytes. To calculate the checksum, add the data in the series and drop the carry, if any, and take its 2's complement of the total sum. The data integrity is checked by adding all the bytes including the checksum byte. The result of this operation must be 0. If it is not, the data is corrupted. With this, I will conclude this lesson. See you in the next lesson. Until then, keep learning.